Today we're going to talk about another concept with which you should be somewhat familiar. We're going to talk about orthogonal projections. Now with vectors, you know that the orthogonal projection of one vector onto the other is the right angle projection. So if you have it going up, it's projected down the right angle one. In calculus, we talked about putting a light above it and where your shadow would fall. If you put the light at a 90-degree angle above it, it's where the shadow would fall. So we've talked about it from the vector standpoint. So we're going back and we're going to introduce the concept with vectors in really R2 on the plane. Then once we do the vectors on the plane, we're going to extend it into any vector space. And we'll even talk about functions that are orthogonal to each other, or functions that have orthogonal projections onto the other one. Okay, now let's go back and consider the plane, R2 or the plane. We have a vector V, we have a vector U, and the angle formed between the vector U and the vector V is theta. The orthogonal projection of U onto V is going to be this vector. So again, think about putting a light up here at the right angle. Where would the shadow be? So the light would come down straight through, so the shadow would be over here. So that's your projection. So we're projecting U onto V. Now, as you can see in the diagram, the orthogonal projection of U onto V is equal to AV for some scalar A. Because as you can tell, the AV and the V are parallel, or your projection of U onto V and V are parallel. Now keep this figure in mind and recall that cosine of theta is the adjacent over the hypotenuse. So since cosine theta is the adjacent over the hypotenuse, cosine theta is going to be the norm or the magnitude of AV divided by the norm, the length or the magnitude of U. So we'll see that cosine theta is the length of AV divided by the length of U. Well, we already know that cosine theta is U dot V divided by the length of U times the length of V. So I replace cosine theta by what it is equal to. Or, if I solve for the length of AV, I would just multiply through by the length of U. Well, if I multiply through by the length of U, I cancel these two out. So I get the length of AV is U dot V over the length of V. Now let's write it as a vector. So the vector AV will be U dot V over the magnitude of U times the unit vector. So what I'm doing is I had the length of AV here, but I'm going to add direction. So the way I add direction and put it in the same direction of V without changing the length would be to multiply by the unit vector. So the unit vector would be the vector divided by its length. So AV would be U dot V divided by the magnitude of V times the unit vector V over the magnitude of V. Or I get that AV is U dot V over the magnitude or the length of V quantity squared times V. Well, we know that the magnitude or the length of V quantity squared is V times V. So we get that the projection of vector U onto vector V is U dot V divided by V dot V times V. Now you're saying, well, what type product is this? Is this scalar? Or, I mean, is this dot product, or what type product? Well, it's just plain multiplication, because U dot V is a scalar, V dot V is a scalar, scalar divided by scalar is a scalar, so all this is just a real number. So it's that real number times the vector V will be the projection of U onto V. Give the orthogonal projection of 5, 3 onto 5, 2. So it's 5, 3, or I'm sorry, 3, 5 onto 5, 2. So we'll call this U, call this one V, and we can say that the projection of U onto V is going to be U dot V divided by V dot V times V. So it's going to be 3, 5 dot 5, 2 over 5, 2 dot 5, 2 times 5, 2. Well, this would be 15 plus 10 over 25 plus 4 times 5, 2. 25 29ths times 5, 2. Or I could write it as the vector 125 29ths 50 29ths. Let's see what we're talking about when we have the orthogonal projection of 3, 5 onto 5, 2. And I'll just do a rough sketch. So the vector V is 5, 2. So here is the vector V. The vector U is 3, 5. So we're coming up 3, up 1, 2, 3, 4, 5. So it'd be somewhere there. Well, the projection, I'll draw the right angle down. So this is the right angle. And this vector is your projection. Well, if we were to change this to a decimal and count over and count up, and if I had drawn it to scale, you'd see that they would match. Now let's extend the concept of orthogonal projection into all vector spaces. So we'll call this the general definition. Let U and V, V not equal to 0, be vectors in an inner product space V. The orthogonal projection of U onto V is given by, this is symbol, the projection of U onto V is equal to the inner product of UV divided by the inner product of VV times V. So it's the same definition, except rather than dot product, I'm using inner product. Look at an example. The inner product for matrices A and B is defined as 2A11B11 plus A12B12 plus A21B21 and so forth. This is the same definition that we used previously. So we're multiplying corresponding components together. We're doubling the first one and the last one. Well, we want to find the orthogonal projection of B onto A. Well, this is going to be B, A divided by A times A. Now notice I'm asking for B onto A. We've been using U onto V. So the one you're projecting onto is going to be the denominator. I'm projecting onto A. So A is going to be the denominator, A times A. And A is what I'm projecting it onto. So A is the one that gives the direction. Well, B with A is going to be 2 times the product of the first two, so that's 0, plus the product of the 3 and the negative 2, that's going to be a negative 6, plus the product of the 4 and 1, that's 4, plus 2 times the product of negative 2 and 1, which is negative 2, over, now A times A, it's going to be 2 times the product of negative 1 with negative 1, which is 1, plus the product of 3 with 3, which would be 9, plus the product of 4 and 4, which would be 16, plus 2 times the product of a negative 2 and negative 2, which is 4. With 2 times 0 is 0, that would be negative 6. Well, 2 times negative 2 is negative 4. 4 and negative 4 is 0, plus negative 6 is negative 6. 9 and 16 is 25, plus 10 is 35. 2 times 4 is 8, plus 2 is 10, and then plus the 25 is 35. So we have a negative 6 35ths. Now times, I didn't bring my A vector down, but this would be times A. This will be times A. So it's going to be a negative 6 35ths times the vector, negative 1, 3, 4, negative 2. Now, of course, I could use scalar multiplication, and it would be 6 35ths, negative 18 35ths, negative 24 35ths, positive 12 35ths. So I could write it as fractional components, or I can leave it as the matrix times the scalar. Let's look at another example. The inner product of f with g is defined to be the definite integral from a to b, f of x, g of x dx. F of x is sine x, g of x is cosine x. F and x and g of x is defined over the vector space of all continuous functions over the closed interval negative pi to pi. Find the projection of g onto f. Well, the projection of g onto f would be the inner product of g f divided by the inner product of f with f times f. Well, this is going to be the integral from negative pi to pi, and the g is the cosine x. Cosine x, f is sine x dx, and for f times b, integral from negative pi to pi, and the f is the sine x, so this would be sine x dx times f. This would be sine x. So this is a scalar. Scalar divided by scalar is a scalar, as long as the denominator is not 0. And times the sine x would be the projection. Well, of course, we could do these by hand, but I decided to use derive. So I went to derive and I authored cosine x times sine x and did the integral and evaluated it and got 0. Just to make sure my projection was defined, I also did the denominator, authored it, and got pi. So as you can see, the first integral is 0. The denominator is pi. So we would have 0 over pi sine x, which is 0. Now this should give you a little more idea of orthogonal and what we mean as we expand the concept of orthogonal into vector spaces other than in space. Think about the functions cosine and sine. What do you know about the two functions with respect to phase shifts and so forth?